And so I am recording right now. This is Mr. Bing. It is Friday, October 9th at 1:45 p.m. Liberty High School, room 409, Principles of Engineering in the Project Lead the Way Engineering program. And we are looking at the assignment, which is 1.2.4, the circuit calculations. This is the last problem in this assignment, and it is by far the hardest. And I have not rehearsed explaining the solution to this problem, but I'm hoping that I will impress all of you by just doing it right on the spot. And that's partially untrue because I actually have prepared my schematic on paper, but as far as where this calculation is going to go, I'm not exactly sure. So close your laptops, please, Matt, and get over here, Nasim, and look at the big screen and look at the circuit. And what I want you to feel, and if Al were here, Louis, Al sits in your seat. And yesterday he would have asked the question, is this a parallel circuit? And the answer is yes. And does that mean that it operates differently? And the answer is heck yes. It operates very, very differently than the series circuits that we have seen. This is where it gets to its most complicated level. If you have, Ms. Hoffman has arrived. Ms. Hoffman, everyone. Ms. Hoffman. By the way, for those of you viewing at home and watching this recording later, Ms. Hoffman, my beloved friend and chemistry teacher, has arrived. You want to say anything to the recording before we move on? Or
I hope you guys are enjoying your learning experience.
Well, I can tell you that based on the glimmer in Nathan's eyes, I think he is having a wonderful time.
Is that how you're doing it?
Yes.
The glimmer in Nathan's
Glimmer.
eyes. All right, wonderful.
So in this circuit, we know that it's going to be complicated. Al is going to be satisfied in knowing that it is a parallel circuit, and therefore it is going to operate sort of by different rules. The first thing I want to say is that we've got a bunch of information given here, and I don't see a question. Where's the question? And the question is always the same. Solve the circuit. That's not really a question. That's more of a directive. The directive is always the same. Solve the circuit. And you're going to say solve for what? And I'm going to say solve for everything. Solve for everything. We need to know the voltage. Well, that was given. However, we also need to know the voltage at each resistor. Well, we also need to know the current. The current was not given. Well, that's a problem. And guess what? There is a different current at each resistor. And the resistances themselves we are given. So the point of all this is that we need to know the total resistance, the total current, and the total voltage. That's three things if you're counting. And then we also need to know the resistance and the voltage and current at the first resistor, and the resistance and the voltage and the current at the second resistor, and the resistance and the voltage and the current at the third resistor. So I can't keep track of how many things I just said, but it's like 3, 6, 9, 12 maybe of all those things that we need to know to solve the circuit. We have to find everything there is to find. Well, starting this process is, knowing what the first step is sometimes the most difficult part. As I look at this, I can tell, well, the total voltage, that's nice. But I look at these resistances, 1, 2, 3. And what I remember from series circuits is that when you have 3 resistors in series, you just add them together, and that gives you the total resistance. That is not the case in a parallel. Parallel does not work that same way. There's actually a very strange equation, and I know I've shown this to you before. Matt, please tell me that you have seen this before. 1 over R equals 1 over R plus 1 over R plus 1 over R. Is that correct, Matt? Have you ever seen that before? He's nodding yes. He's nodding yes. And actually, this is 1 over R sub T for the total resistance. And this is equal to 1 over R sub 1, 1 over R sub 2, 1 over R sub 3. That is the sum, or wait a minute, let me go backwards. It is the inverse of the sum of the inverses. And there are all kinds of little tricks to doing this. All I'm going to do right now is just plug in some numbers. 1 over R sub T equals 1 over 8.2 kilo ohms is really 8,200 kilo ohms. And then 1 over 6.8 kilo ohms is really 6,800 kilo ohms. And then the last one, 4.7 kilo ohms, is really 4,700 ohms. So now, we could do the 1 divided by 8,200 and get a decimal, and then the 1 divided by 6,800 and get a decimal, and the 1 divided by 4,700 and get a decimal, and then add them together. And then we could solve for r sub t by inverting whatever that sum of those decimals are, whatever the sum of those decimals is. However, my friend Jess, Nassim, you know Jess, my friend Jess sort of got me thinking, and she figured out that there was a quick, easy method on a scientific calculator. And that method is in reference to the 1 over x key. I don't know how well you can see that. I'm zooming the wrong way here. This right here, I know there's a strange glare. This, right, there's the 1 over x key. That's a little 1 divided by x. And so the way this works, if I start over with 0, the way this works is that if I have 1 over 8,200, tricky. If I have 1 over 8,200, I can just push 8200 and then the 1 over x key. And that automatically gives me the decimal for 1 over 8,200. But then I can plus the next one, which is 6800 and 1 over x key for that one. And then plus 4700, 1 over x key. I've done all three now, equals. So that's the sum of the three inverses. And now because this 1 over r sub t, it has to be inverted. And so the 1 over x key is going to do that. And so 2076, it looks like 2076 is the total resistance. R sub t equals 2076 ohms for the total. That is one of the 12 things we have to know. Well, there's 11 to go. Yes, yes, thank you. There's 11 to go. I'm not done, but I probably need some sort of break. So I'm going to stop the video and we'll do another part of the video in just a moment. I'm going to click end and